In this video, I'm going to take you through a very typical sort of static equilibrium problem. Static equilibrium meaning everything is stationary, and according to Newton's first law, therefore all the forces are balanced. You need to begin always with free body diagrams of your situation. This is a very typical sort of question where you've got some kind of mass hanging from a collection of ropes. In a situation like this, you'll need to make a free body diagram for the place where all the ropes meet, for the knot. So this is what the free body diagram for the knot will look like. You've got the force of tension in rope A, force of tension in B, and force of tension in rope C. The other free body diagram is for the mass, which is also in static equilibrium. There is a force upwards. Now this rope C between the knot and the mass, one characteristic of tension in ropes is that it's the same tension all the way through. So the FC hanging down from the knot is the same FC holding up the mass. And then, of course, you've got a force of gravity downward. So we're going to start analyzing these forces, and we'll start with the easy one. We'll start with the mass, because there's a lot less going on here. When an object is in static equilibrium, all the forces balance, or another way of saying that is that the net force, or the summation of forces, is equal to 0. So in this case, we've got two forces. We've got the force in rope C and the force of gravity adding up to 0. Now this is possible, of course, because they're acting in different directions. And when we substitute for the forces, we can use plus or minus signs to indicate the direction. We're going to use a coordinate system like that for x and y, where the positive is to the right and up. So that means that force C is positive, force of gravity is negative, because it acts down. And in this simple equation, they must be equal to each other. So Fc is equal to the force of gravity, and that, of course, is m times g. The mass of that mass is 5 kilograms. I insist on giving it another significant digit there. G, 9.81 meters per second squared, which is 49, and I'll throw in a couple more decimal places there in case it matters. So we've already solved for one of the tensions. Now let's move on to analyzing the knot. And again, for the knot, the net force, the sum of all the forces, is equal to 0. But you can see this is more complicated because now you have forces in the x and y directions. We're going to handle the x and y components separately. So the first thing we'll deal with is that the sum of the x components is 0. Now, forces B and C, they line right up with axes, but A doesn't. So let's draw in components of A. So we've got FAX and FAY. It was given in the problem that this rope A is hanging at a 37-degree angle, and by Z pattern, that means this angle must be 37 degrees as well. All right, so our x components all add up to 0. So FA x component plus FB x component plus FC x component all add up to 0. As we make our substitutions from the diagram, though, we have to pay close attention to what's in the positive and negative direction. So let's start with the x component of force A. It's to the left, so it's going to be negative. And it's going to be the force of A multiplied by the cosine of 37 degrees, because this component is adjacent to the 37-degree angle. So we've got negative FA cosine 37 degrees. Okay, now for force B. Well, you see how it's lined up with the x-axis? Its only component is in the x direction. So you don't need to use trig or anything. We'll just say that the x component of force B is force B. And then for the x component of C, well, you can see force C is lined up with the y-axis. It has no x component. So it's gone for now. From here, FB is equal to FA cos 37 degrees. All right, that's useful, but it doesn't solve for force B or force C. So we'll be coming back to that after we look at the y components. So all the y components also have to add up to 0. Formally here we write FAY plus FBY plus FCY equals 0. So your y component of force A, it's up, so it's positive, and it's opposite the 37-degree angle, so we're going to use the sine of 37 degrees. So FA sine 37 degrees. Force B is all in the x direction. It has no y component, so it's gone. And then force C is along the y-axis. It is entirely y component, so we'll use negative because it's down, and we'll just substitute FC there. And now we're making progress because we know FC. We've solved for that from the free body diagram for the mass. So let's substitute in that value. Here, if we call that line 1, and we substitute for FC, then FA sine 37 degrees is equal to 49.05 newtons. And you can solve that. That's going to give you FA is 81.5 newtons. All right. We're moving here because we can go back to this line, which we'll call line 2. And we'll substitute that result for FA in our statement from line 2. So then FB is equal to 81.5 newtons times cos 37 degrees. Oh, and that makes total sense because that is the x component of force A. And you see force B and the x component of A have to be equal to each other for this to be an equilibrium. Similarly, as we showed, the y component of A has to equal the force in rope C. Okay, we're almost there. So FB is 65.1 newtons. We are solved, and we'll just write a therefore statement. Therefore, the tensions in ropes A, B, and C are, and we'll need to get these all down to 2 significant digits. So A is 82 newtons, B is 65 newtons, and C is 49 newtons, respectively. Okay, so to recap, static equilibrium means the net forces are zero. You need to draw free body diagrams of the important points in your equilibrium situation, in this case, the knot and the mass. And then for each one, you set the net force equal to zero. If you're operating in 2 dimensions, and in the case of the knot, you will treat the x and y components separately. And you should have enough information to make you solve for everything that you need. Okay, have fun with these.